Okay, next video, and it's a fragile ecosystem and megafaunal extinction. Page 6 out of 17. And again, a bit like the last one, we're kind of warming up a bit here really, and we're not looking at policies and stuff, although we are actually, from this one, I will discuss a bit of policy conclusions and conclusions we can draw from this to the present day management. So yeah, this is kind of an interesting one actually. More policy relevant than the previous one, which was more a bit of fun really. So let's see, slide 7. Oh yeah, so this is a bit of an intro. This is a picture I put in one of the first papers I ever published back in the 90s, which is taken from a paper from 1990. What can we say about this? There's different ways of looking at the management of nature. Top left picture, nature capricious. It's like nature's the ball. It could go anywhere. We can't control it. It's the sort of fatalists worldview. The little man, the little guy, can't do anything. No point in trying to do anything. Then there's the bottom right, nature ephemeral. That's like the eco warrior kind of look. We do the slightest thing wrong, it's disaster. We have to be incredibly careful. It's kind of or. Then there's the individualist, bottom left. Nature's benign. We can muck around with it, anything we like. It'll always go back to equilibrium. Things will be fine. Go ahead, free markets. Let everyone get on with it. And then there's the top right, which is nature perverse, tolerant. That's the hierarchist, or if you like, the environmental economist. It's like nature. It's pretty cool, but if we push it too far, we could have disaster. We need management. We need models analysis. And that's what we're going to do here. Trying to explain megafaunal extinction as the regrettable result of bad management of the resource. Okay. So the first point to make here, so how are we going to model megafaunal extinctions? So according to what I claimed in what I guess was the previous lecture, or in the intro chapter of the book anyway, these megafaunal extinctions, they seem to happen pretty fast. And technological progress in those era where the megafaunal extinctions were taking place is what we call in UK English glacial, very slow. Okay, so during the time the megafauna got extinct, or any given animal got extinct, technology will hardly have changed, right? If it took 200 years or 1,000 years or whatever to get the animal extinct, technology is hardly changing over that time scale. Way back when? 10,000, 20,000, 30,000, 40,000 years ago, depending on which megafauna we're talking about. So that's kind of cool. That's a relief. We can treat technology as constant. That makes things a bit easier, doesn't it? And then what we're going to do is build what is known as a predator-prey model. Humans, and this is like the fox and the hare. And in the predator-prey model, you typically assume that the predator is totally dependent on the prey. And we'll see what happens in that case, and then we'll start thinking about alternatives. So, slide 9. Sorry, got a touch of the hiccups. What have we got? We've got Y is harvest, L is population, humans, N is the megafauna population, and we have what we call a linear harvest function. So we have Y is phi times L times N. So what does this mean? Y is the amount of harvest, phi is a number, what we call a parameter, as you know, L is the number of humans, the number of hunters, N is the number of animals. So if you double the number of humans, you'll double the harvest. You'll double harvest. If you double the number of animals, you'll double harvest. So the tricky thing with hunting is finding the animals here, isn't it? Because if you double the number, they're twice as easy to find. If the tricky thing was killing them, then you might think y should just be phi L. Or it would be closer to that anyway. Of course, you need some animals. But if it was trivial to find them but hard to actually kill them, then you would have this n raised to some small number perhaps. But here we're assuming the tricky thing is finding them. Okay, and then we have a variation of the logistic growth function for the human population, but I have a slightly simpler formulation compared to the previous model. This formulation saves some equations, and I think it makes more sense actually. I should really have had it in the previous model too. So we have theta L LT. So theta L is the maximum growth rate of human population, yeah? And then we have 1 minus y bar over yt over lt. So yt over lt, that's consumption per capita, isn't it? And y bar is, I guess, we'll find this out shortly, but if we assume, let's think y bar is probably, like in the previous one, is what a human needs to survive, right? Is that right? Well, so if this is equal to y bar, then this is 1 and this is 0, population growth is 0. Yeah, so that makes sense, doesn't it? When we're getting just enough to eat, the population is stable. But if this is more than y bar, then this is bigger than this is less than 1, then this is bigger than 0, and we have growth. If this is infinite, so we've got all the food we want, then this is 0, this is 1, and we have maximal growth rate, theta. LT plus 1 minus LT over LT. That's the percentage growth per period, right? Okay, so this makes nice sense, yeah. Oh, and if this is less than y bar, this is bigger than 1, the population will shrink. So this is actually a simpler way of formulating the logistic growth function when technology or consumption per capita is changing or might change. But of course from this we can say, oh, but look, y over L is phi n. So we can stick phi n in here, can't we? Okay, and this is the equation, still on page 9, for the dynamics of the human population given the animal population. So we can say straight away, when n, the animal population, is equal to y bar over phi, the human population will be stable. But when is the animal population stable, yeah? To get a steady state with both stable, they both need to be stable. So, what about animal growth? Animal growth is standard logistic, so that'll be theta n nt 1 minus, let me see, what's my notation going to be here? Let me check. Yeah, I'm going with this star notation. Nt over n star. So this will be if there's no harvest. Those of you who are doing or have done management of biological resources will recognize this. Same sort of properties as this, but slightly different way of formulating it. This is, what do we call this? Carrying capacity. If population is equal to carrying capacity, growth is 0. If population is less than carrying capacity, growth is positive. Population is over carrying capacity, growth is negative. But in addition to this growth, this intrinsic growth of the population through their eating and whatever, we also lose individuals through hunting. And how many do we lose? We lose phi L N, don't we? So those are our two equations describing the dynamic system. And it turns out, so this isn't much of an economic model really, is it? Because there's no optimization or whatever. We're just saying, look, humans go out there and they hunt for all they're worth. Okay? So there's no optimization by the humans going on here. They just go out and hunt. All their time they spend hunting, and it's like, if they catch a lot of, manage to kill a lot of animals, then they've got loads of food, loads to go around, the population will go up. Okay, this is what we're assuming here. So basically we're done. There's no first order conditions, no nothing. I guess it's similar to the previous model in that sense. So then we can just basically stick these two equations into MATLAB or any other model. You could stick it into Excel if you wanted. And then we have some starting conditions, and then we run it. And what do we find? So we have time here, and this is like hundreds of years. And we have like populations here. And I think we kick this off, we're assuming that humans arrive. This is like humans have just arrived in North America. They crossed over the Bering Strait. Yep, from Russia, or it wasn't Russia then, but so there's only a handful of humans and there's loads of megafauna. And it's like, wow, it's Christmas. Yep. So what happens, the humans kill the megafauna like crazy, and they eat like crazy, and the megafaunal population goes down and the human population goes up. But then at some point they find that they've run out over the cliff edge, yeah, and they look down. And then, because it's like, oh my god, we've killed all the megafauna, and there's loads of us. We can't maintain these harvest rates. We start to starve. Okay, so the humans starve. But the megafauna populations are still going down for quite a while yet. But when the human population drops below, gets low enough, then their harvest rates will drop, plus the megafauna are harder to find. Remember, it's all about finding the megafauna is the problem. The megafauna population drops, they're hard to find, there's not many humans anyway. The megafauna population starts to recover. Megafauna population recovers, well then with a lag the human population is going to recover. So we end up with the one lagging the other. So which is behind? It's the fauna is behind the humans, isn't it? And you could set this up so that it would look like this and would never settle down to an equilibrium. The way I've set it up, actually we head towards an equilibrium, and there is a steady state where both populations are constant. Of course, in reality, other things are going to fluctuate and you will never settle down to that steady state. But we do see these fluctuations in reality. Populations of sort of foxes and hares or whatever do fluctuate in this way. I guess we probably don't know. I don't know if there's any evidence for human populations fluctuating in this way. Probably not. Why not? Have a think about that. Stop the video if you like, and before I carry on. Okay, So why doesn't it look like this? Well, one important reason was that humans are generally not dependent on just one species, or not even largely dependent on a single species. We're incredibly adaptable, right? As a species, we're like rats. We're amazingly adaptable. So if one species starts running out, we'll find something else. Not always, of course. There can be famines and so on, obviously. But we are amazingly adaptable. Okay, then there's a question here, slide 11. Oh, I'm not ready for this, I might have to pause the video. What's the maximum sustainable human population? Why don't we get there in the simulation? Well, I'm wondering if I should go through this or whether if I should leave this to you guys as an exercise. I think I'll leave it to you guys as an exercise. So we'll talk about this on Zoom at some point. So have a think about that. What's the maximum sustainable human population? So just to give you some hints, humans need Y bar, don't they? So if you assume there's some maximum population, you could call it L superscript n. If you assume that, and you know that each one of them needs Y bar, you could work out what the harvest would be, couldn't you? And then you can relate that to this. Yeah, I'm not going to say any more. I think you should be able to work that out. Why don't we get there in the simulation? Yeah, have a think about that too. I'm not going to say anything about that. The model doesn't lead to extinction. Why not? Oh, this is perfect. I hadn't planned this, but this is great. I'm not going to answer that one either. Okay. We can talk about it on Zoom. Why doesn't the model lead to extinction? What is it about the model? How could we adapt it to lead to extinction? To deliver extinction? Well, actually, yeah, we won't talk about this on Zoom because the next step is carrying out such an adaptation of the model. So, I think that's the last slide. Yeah. So have a think about that. Why doesn't the model lead to extinction? How can we adapt it? Before you check the next video, because you're going to find the answers to those two questions in the next video. But the previous two questions from slide 11, I'm not going to answer on this video. We're going to talk about it in Zoom. So think about those. Okay, see you soon.